Welcome to the online global classroom, jointly organized by Faculty of Science, University Technology Malaysia, and Guru Jambheshwar University of Science and Technology, Hisar, Haryana, India. I am Shiv Krishna here. The theme of this webinar is Fundamental Science, Bedrock of Innovation. I am thankful to the Faculty of Science for giving me this opportunity to introduce our eminent speaker today. And particularly, I'm thankful to the head of the Department of Physics for giving me this chance. I am pleased to introduce today's speaker, Professor Devendra Mohan from Guru Jambheshwar University of Science and Technology, India. It's very difficult to describe him, or rather his academic career of 35 years or so, in few minutes. But I would just like to tell that I had an opportunity to work with him closely as colleague for 5 years, and since then our collaboration is on. Professor Mohan is a renowned academician with great caliber and knowledge in the area of laser technology, nanophotonics, fiber optics, and many other areas. He acted as dean, chairman of the department for a few times. Today, the title of his talk is Scope of Photonic Technologies in Current Era. Having said that, I would request Professor Devendra Mohan to deliver his lecture. More you will gain from his talk. Thank you. Please welcome.
Thank you, Dr. Vishal, for the fine introduction. I think my voice is clear to you.
Yeah, clear. Please go ahead.
I'll go ahead. So I am thankful to the as well as the head of the Department of Physics, Malaysia University, and our colleagues who have joined from your place, and particularly Noor Hafiza, who has been in between connecting us, timings and all slots. So with this kind introduction, I will go directly to my presentation. So let me go this. Since your theme was innovations, so I thought of giving a talk on the latest development in photonic technologies in current era. Vishal, my slides are clear?
Yes, your slides are clear. You can change to presentation mode, maybe?
Yeah, these are presentation mode.
Yeah, so fine, fantastic, very clear.
There was a theme of scope of photonic technologies in current era, and you wanted to innovation. So I have tried to give some idea of the photonics going in this technological era. So my outline of talk will be photonics in general, and why do we need an alternative to electronics, and how is photonics better? And then I'll switch to one application, optical damping and switching in photonic materials, and then I'll conclude. So if human beings are the highest form of God's creation, the internet is the highest creation of the human mind. This is from seeing the divine in digital technologies. We all worship various objects, but we basically are not worshipping the objects, but the divinity immanent into these things. So internet has been one of the most important digital technology of this era. When the COVID-19 pandemic unexpectedly disrupted our lives and shook us out of our comfort zones, something paradoxical happened. Despite the constants of lockdowns, we have become more closely connected globally and locally, thanks to the magic of digital technologies. So the today's world is an era of technology, and this technology is constantly changing. Just as electronics is the technology of the 20th century, photonics is the technology of the 21st century. Even though the photonic era began in 1960 with the invention of the laser, it became an impact on telecommunication only in late 70s. So, I would like to dedicate today's lecture to Narendra Singh Kapani, who is known as father of fiber optics, and he only few days before, only December 4, 2020, and Narendra Singh Kapani is known as father of optics, and he was the person who can bend the light through fiber optics. But some missed the Nobel Prize. Nobel Prize was given to Charles Tao, but his basic building block was Narendra Singh Kapani. So, what is photonics? Photonics comes from photon, which is the smallest unit of light, just as an electron is the smallest unit of electricity. Photonics, in general, is the generation, process, manipulation of photons to achieve a certain function. Light is thousands of times faster than electrons in computer chips. So it is the velocity of light which makes it particularly important that we can use light on the photons instead of electrons. Optical computers will compute thousands of times faster than an electronic computer can ever achieve due to physical limitation of difference between light and electricity. And this can pack more wavelengths, so we can use more information channels. So photons replace electrons to offer light speed, super energy efficient data processing. Why do we need an alternative to electronics? One may ask. The problem we are facing is that the handling and processing of data, which we do in data centers, is still done by microelectronics, and microelectronics is not very energy efficient. In 2016, all electrical power generated was used for processing data in data centers and telecommunication centers, and that is growing with a factor of about 1.7 per year. So also with the Internet of Things, Netflix, Facebook, YouTube, and other internet activities, we all are using all these apps nowadays. And data centers are growing capacity by a factor of 2 per year. So microelectronics is a limiting factor. If we want to grow traffic at the same rate, it has been growing for the past 20 years. So we need to do something different very rapidly and fastly. So how is photonics better? Looking at the energy efficiency of the most advanced microelectronics chip, processing a bit of data consumes roughly a picojoule. When a photon-based technology is used, the energy budget is less than a femtojoule per bit. So a factor of 1,000 less energy is demanded. So the other advantage is that when we look at the frequencies we can cover with photons, they are a factor of about 1,000 to 10,000 higher than the spectrum. So we can cover with electrons. So we can go to much higher frequencies and we can do that far more energy efficiently. So that is why the photonics is better than electronics now. Now, what can we do with photonic circuit that we cannot do with microelectronics? We cannot do everything only with microelectronics, so we couple our light sources with that. And the one major example is LIDAR, light detection and training, where we have replaced the, it is similar to radar, where we have replaced the radio waves with light waves. So radar is radio detection and training, and LIDAR is light detection and training. So driverless cars, has been the fantasy of 1990s, and you must have seen certain English movies, The Love Bug and Demolition Man, where driverless cars are being used. Since it has been the fantasy in 1990, but today, December, I must tell you that this is coming to reality. I will tell you the news that the permission has been granted to one firm to go ahead with the trials of the driverless cars. So what is LIDAR and how it works? So one need to understand it. So LIDAR, as I told you, that this is light detection and training. there will be GPS system, there are cameras, there are sensors. As we know that this is the era of robotics and sensors. So this is one monodiagram of use of the LiDAR. Now, what are the components of LiDAR? There are 5 important components in this. One is the use of the laser source. So far in LiDAR, we are using a jar laser, either 532 or 1064 or both. And scanners and optic system is there. This projects laser pulses to surfaces and receiving back the reflected pulses from the surface. So the speed at which images are developed by a LiDAR system is dependent on the speed at which the scanners capture the backscattered beams. So the forward and backward image both are important. So the processor integrates the data from the timer, the GPS and IMU to produce the point of data. So these elevation point data are then used to create maps depending on the application. So in driverless cars, the point data is used to provide a real-time map of the environment to help the car with the obstacle awareness and general navigation. So accurate timing electronics is one of the important component of this LiDAR system to record the exact time a laser pulse leaves and the exact time it returns to the scanner. So internal measurement unit and GPS system is also one of the technology which lastly developed and we all are using in our vehicles to determine the absolute position and the orientation of the sensor to retain usable data. So the processor has to be very fast, integrating all these electronics, accurate timing electronics and inertial measurement along with the GPS system. So LiDAR uses light across different wavelengths. LiDAR can use various wavelengths. Either it is ultraviolet, it is visible or near infrared to image the objects, and it's such that able to detect all kind of material compositions, including non-metals. Our purpose is only when it can detect all types of materials, whether it is non-material, rocks, rain, chemical compounds, aerosols, clouds, and even single molecules. This system could fire up to 1 billion light pulses per second and use the time taken for the pulses to be reflected back to the scanner to determine the distance at which objects and surfaces around the scanner are located. So the technique used for the distance determination, we know. We have gone through undergraduate level that how to measure the distance. It is speed of time of flight by 2. So by using the technique of time of flight, we can calculate the distance. So this is the news I was telling you, that this is the today's news. So I have put the slide over here that Baidu become fully driverless road test permit in Beijing. So Baidu has become the first to receive the permit by the Beijing Transportation Authority. So you can see that this is similar to the picture what we have seen in the earlier slide. So another aspect of now coming to the fiber optics communication link, you just look at the picture. What is there? What we need for the communication is transmitter, then guiding medium, and then the receiver. So first we have a transmitter. We use the laser source as a carrier waves, and these are the electrical pulses. Now these transmitter converts our electrical signals into optical signal, and this optical signal goes through the waveguides or the optical fiber, whatever we call optical fiber or waveguide, one and the same thing. And then because of some limitations of the optical fiber, there is a dispersion, there are attenuation, so we get the attenuated signal, and then we have the photodiode which will detect these optical pulses, and this photodiode will convert optical pulses into the electrical pulses, and then these electric pulses are amplified and we get the final signal after the decision circuit and the processing unit as voltage pulses or the amplified signal. So this is how the communication system works. Now this is slide mentions you about the circuit after the photodetector. So there are filters, low pass filter, high pass filter, band pass filter, in order to make corrections in the distorted pulses or the waves, whatever has been there. So important concept in this is that that we need to look into the power budget, what power we are launching and what we are getting. So there is a loss of power at different stages of this. When we in the initial state we are coupling laser with the fiber, and at the output fiber with the detector, and the points are source to fiber coupling loss, then fiber which has some attenuation characteristics, then splicing loss. If we are making fiber to fiber joints, if we are making the length of the fiber large enough, then we need to go for the splicing of the fiber. So at the joint we have the splice loss, and then fiber to detector coupling loss, and the optical power transmitted and received are expressed in dB decibel meter, whereas the reference power is somewhat milliwatt, megawatt, whatever it is. So if we go for the calculation, if we consider the source power as P0 dB meter and minimum power required at the detector is Pi, so what is Pi? Pi is equal to P0 minus Pn. P0 is the total power, whatever we have, and source to fiber coupling loss is L1, and number of slices if we are making is N, and average loss at each splice is Ls, and total loss due to splices is then N multiplied by Ls, and fiber to detector coupling loss is L2, and fiber attenuation if we consider as Lf, and total fiber length if we consider as D. We need to multiply this D by the fiber attenuation, and then power margin. Some margin we need to keep for extraneous losses, which are hidden losses, which are due to aging of the components, that is Pm. So Pi is equal to P0 minus Pm, and adding all these losses, one can find out the power. We can do the power budgeting in this way in a communication link. So this is the communication link. I have told you that there are joining of the laser with the fiber and then fiber with the detector. So fiber has the splicing. So at every we have calculated the losses, and we have gone for the margin of the power. That now fiber itself has the higher dispersion, so we need to use the low dispersion fibers. That is one very important point, is that we will be using low dispersion fibers. Designing large bandwidth optical fiber communication system, the rise time of the components. Now here, the rise time of the components, that means particularly of the receiver circuit, where we are using the photomultipliers or the photodiodes. The rise time of these detectors is very important, that the response time should be compatible. So thanks to the electronics engineer who could face up with the optical engineers to give us the handy photodetectors. So how to build? Now we want that the losses minimize. If losses has to minimize, then we need to leave away with the conversion part, either from electrical to optical or from optical to electrical. Can we go for the 100% removal of these joints? No, but certain things can be done. That if we look at a microelectronic circuit, we have active components in that, which are the transistors, and we have the passive components, resistors and capacitors. With those three building blocks and the electrical wires connecting them, we can build any type of functionality. But for photonic integration technology, we also have basic building blocks, which are optical amplifier, a polarizer, a phase shifter. Of course, there are many components being developed, and I must name the optical isolator. So I have been told that something went wrong. Yeah. Okay. Am I audible, Dr. Bhatal?
Yes, nothing wrong. It's okay.
Okay, okay. I got some message from my colleague that something like that. No problem.
No, maybe their system here. Okay, everything.
Okay, 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 okay. I'll continue. So I need to go back. Okay, no problem. So So I was talking about the various components which are required for photonic integration technology, similar to the electronic components, where transistors and passive components were the resistors and the capacitors, and with these three building blocks, the microelectronic chips were working. But for photonic integration technology, we have to go for optical amplifier, a polarizer, and a phase shifter. And most important is the optical isolators. So with those three components, together with a light guide wave, which is the equivalent of an electric wire, light guide wave. That means we were talking about the optical fiber. So we can engineer any functionality to build any type of processing you can do with microelectronics. So the only difference is that the information is going to be photon instead of electron. So next question is, what is holding up photonic deployment? If we look at photonic integrated circuits today, the complexity is comparable to the complexity the microelectronics industry was facing in the mid-1970s. So the similar type of complexities, this technology, which is likely to come up in the years to come, that is photonic integration circuits, similar complexities we are facing. So that means we can integrate about 3,000 components onto a single circuit. So it is not a very high integration density when you can integrate billions of components into a single microelectronic circuit. So one of the major challenges we are facing is the increasing photonic integration density. So now for silicon, we have a lot of infrastructure built up all over the world. So where does silicon will fit into this technology if it is so silicon has been a very attractive material for photonic applications so far due to the fact that we have an infrastructure for processing it with very extensive factories all over the world that can mass produce silicon-based circuits. But from an application point of view, silicon is not attractive at all because it has the highest losses. The losses are at least a factor of 10 higher than in case of indium phosphide. And you cannot produce active components. So you will always need another material connecting to these silicon-based photonic circuits to get light into the circuit. So the only problem with indium phosphide is that as a semiconductor material, it is not as far developed as silicon is. So it requires further investment in basic infrastructure to provide indium phosphide materials and circuits based upon them at scale levels comparable to what we have been doing with silicon today. So these are the major challenges what we have in replacing the silicon. So what kind of challenges? So if we look at how we want to move forward, in the area of preventive healthcare, we need to be able to detect illness like cancer, for example, at a very early stage and at low cost. And the sensor systems that can do that, detect cancer, monitor your blood, and photonic integrated technology based can help us. When you look at smart cities, one of the key things is the control of air pollution, and the sensors we need for that are photonic integrated circuits that can provide that functionality at low cost. So there will be many applications we cannot dream of today. So where will the first application of photonic integrated circuits will be then? The first application we can see is, of course, in the communication. Think of communication speeds. Now we need to increase the speeds of 400 GB per second across optical interconnects as soon as possible and rapidly growing to 1 to 2 terabytes per second in the coming years. So which can only be realized with photonic integrated circuit technology. So the same applies if the world is ready to switch over from 4G to 5G. So we need to replace the current base stations with something much smaller and far less energy demanding that can handle much more traffic. So which means we have to use optical technology. So I expect that photonic integrated circuits will be the next generation technology that will be used to solve many of the challenges the world faces. So coming to the next part of my talk, where if we are using the high power lasers, we need to protect the devices as well. We need to protect the sensors as well. Our eye is also a sensor, and we need to protect it. We use glasses, but these have certain limitations, as of changing focal length, as of astigmatation in ordinary optical components. So we have the limitations of using the optical components. So we need to develop optical limiters or optical switches, which converts from optical to electrical or to optical, or sometimes all optical. So we would like to remove the conversions of from optical to electrical or from electrical to optical. So in this, nonlinear optics is going to play a very important role. So one or two slides I have put, which will let us understand what is nonlinear optics. It is the study of interaction of intense light in matter. So linear region, if we talk about the linear region where our refractive dependent of the light intensity, but as intensity, particularly we talk about the laser sources, and these have the high intensity, high power. So it depends on I. N is equal to N naught plus N2 I, where written this E square of T, amplitude of this. So this can be replaced with I. So as I is increased, we reach to the higher order terms. We need to consider higher order terms. As we know, the material is polarized, and polarization is written as epsilon chi1 E chi epsilon 2 E plus chi 3 E cube, and so on. And for a photon, if you consider E is equal to E naught cos of omega t, a term E square as E naught cos square of omega t. And applying our basic knowledge of trigonometry, we use it to double angle, so cos of omega t upon 2. So that means you are getting second harmonic. So if you can find out some material, a fundamental light is falling on it, and you get at the output as the double of the frequency. So just the information I have put for the understanding. Acting on a molecule which vibrates and then emits its own light wave that interferes with the original light wave. So in nonlinear optics, just see if variance is high enough, vibration at all frequencies corresponding to all energy differences between the populated states are populated. So in optics, you get a new color. That means new frequency. So if you go for the semi-classical description of light propagation in the dielectric media, where the material constants epsilon are independent of the field strength, and linearity applies that the permittivity experienced by a field with E to 10 volt per meter is the same experience for the strong field of E is equal to 10 for 9 volt per meter. The value of permittivity changes only slightly for these high fields, and this change leads to spectacular effects. So nonlinearity arises from an harmonic motion of the electrons in response to the applied field. So there is a well-established theory of this. I am not going to into the detail of this theory, but I just wanted to tell you the origin of this. So if you go for the origin of the relationship, as light is an electromagnetic wave, it is a combination of both electric field and the magnetic field. So intensity of light is basically the power transmitted through electric and magnetic field divided by the cross-sectional area of that light beam. So we can write down the intensity of light beam. Now the energy density of the electric field is given by half of epsilon E square, and the energy density of the magnetic field is half E square upon mu naught epsilon naught E square, and the total energy density of EM wave is then by this, half of epsilon naught E square plus G square upon mu naught. These relations are not new to you, not new to everyone, because these are the standard electromagnetic theory. So the expression becomes half of epsilon naught E square C. So simply I will go for some tutorial after this slide. What I wanted to convey you that non-linearity plays a very important role as we go on increasing our field strength, and field strength of the order of 10 to the power 9 volt per meter is sufficient to produce to originate the non-linearity. So this picture lets that how the driving wave is interacting with the material and non-linearity arises. So the Fourier theory will dictate us to resolve the various components of this. So nonlinear behavior occurs when the secondary oscillator is given the linear response. As a result, the oscillation becomes non-sinusoidal, as you can see here that you get the nonlinear response after a certain linear range. So Fourier theory will help us to get out of it. So this is our standard equation. So based upon the terms which are used, here you can see the chi2 term and chi3 term. In case of glass, the term of even order vanishes. The term of even order vanishes because glass is amorphous, isotropic material, and there is no polarization, so the even order terms will go away. But there are certain optical phenomena where chi2 can be there in certain materials. We can calculate chi2 effects, and in certain materials we can go for the chi3. Chi is the susceptibility. So second order susceptibility or third order susceptibility. Based upon that, we have certain phenomena which I have penned down. So second order phenomena gives us the second harmonic generation, as we were looking into the previous slide, that we get the new color and sum and frequency, sum and different frequency generation, magneto-optic effect, electro-optic effect, and parametric amplitude. And in case of third harmonic susceptibility, third order phenomena, we get the third harmonic generation, degenerate four-wave mixing, two-photon absorption, stimulated Raman scattering, self-focusing, phase conjugation, electric field induced second generation, laser field induced birefringence, and so on. So my application of today's talk is towards optical limiters using nonlinear photonic materials. So optical limiter is one of the important applications of third order nonlinearity. The background what I was making for nonlinear optics was because in optical limiters we are using the application of third order nonlinearity, where analog materials can be used for protecting sensors against high intensity of the laser sources. So an ideal optical limiter is a photonic device or a component, the characteristic of which is high linear transmission for low output. So it has to process incident light beam. So it should work with either with the continuous wave or pulse wave of any duration. So this diagram will let you know the characteristics of optical limiter, what should be the characteristics of the limiter. Ideal limiter should have low limiting threshold. Look at the curve. Low limiting threshold. It should show fast response time in any of laser. Either the laser is continuous wave, or the laser is nanosecond, or the laser is femtosecond. Broadband limiting response to the entire visible spectrum, and low light scattering inside the material medium. Material should be such that there is low light scattering inside the medium. So the figure shows linear transmission below a threshold level and fixes the output to a constant level above it, thus providing safety protection to sensors, including our human eye. So look at the diagram critically, that we have a linear region, then there is an active region, and then there is a saturation region. So this is the system. Input conditions, we need to look into the input conditions, we need to look into the system requirements, we need to look into the output conditions under the environmental conditions. So input conditions should capable of taking input light beam of any intensity without any material damage. There should not be material damage. So any intensity falling on the material should be safe. Number one. Capable of accepting input light beam without reflection or scattering from the incident surface. There should not be any reflection or the scattering from the incident surface. Any variation in input intensity or power between 0 to infinity should maintain constant output intensity irrespective of input intensity variations. So constant input intensity, as you can see, that if we go on increasing our input power or input intensity, it should go to the saturation level, and capable of accepting input light beam of any wavelength or frequency of entire EM spectrum, and capable of accepting input light beam of CW or pulse beam of any duration. And these are the input conditions. And if we go for the system requirements, high linear transmittance with wide transmission range throughout spectral bandwidth, and transmission characteristics. We know that these vary depending upon the incident intensity due to the NLO properties of the limiting material. And NLO material should have high nonlinearity for entire bandwidth. So high nonlinearity, who will decide the high nonlinearity? In the next coming slides, I am coming to this part. So third order nonlinearity, or the nonlinear absorption, or the nonlinear reflection, how we can measure these, how we can calculate these experimentally in our laboratory. So I'll be coming up in 2-3 slides next. So limiter should work for any power of CW or the pulse. And output conditions, linear transmission the below threshold, and output intensity is independent of the wavelength and pulse duration, and output beam as a high quality Gaussian beam of constant amplitude, as the Gaussian beam as at the input, and similarly at the output quality should be same. Environmental conditions, constant output for any change in temperature, pressure, and aging. They should not be changed. If we take our device to some other geographical locations, the result should not change. So what happens in nonlinear materials? Optical nonlinear absorption. The material can make use of 2-photon absorption property or reverse saturation absorption property and nonlinear reflection property simultaneously. That means I am talking about the two important things, nonlinear absorption and nonlinear index of refraction of the material here. So there are three regions, as I have already told: linear, active, and saturation region. So in order to have the 2-photon process, we need to understand the concept of this 2-photon absorption property in a material. So I am coming to this multi-photon processes. So if we are considering a simple absorption or emission of a photon from one state to the other state, it represents the rate of direct transition from state I to final state F, say. Then for photon absorption process, second order term is required. As you know that we need various terms to be adopted at various stages. The higher order terms also represent transition from initial state to final state, but the transitions are via one or the more intermediate states. I will come to the next slide where I will show the intermediate states. The presence of delta function, and so we need to take into consideration the law of conservation of energy as well as law of conservation of momentum in all the processes. So for a 3-photon process, we have to consider for certain the third term. The elements in this term indicate that the fluorescence resulting from 3-photon absorption must be proportional to cube of the laser output. So there is a difference between fluorescence emission and 2-photon absorption. So the simultaneous absorption of the photons lead to second harmonic generation. So here comes a slide. It is important that second harmonic generation is a 3-photon process. It is a photon process. 2 photons, each with energy H cross omega, are absorbed, and 1 photon with energy 2H cross omega is emitted. Simple. So 2 photons with energy H cross omega are absorbed, and 1 photon with energy 2H cross omega is emitted. So the state of quantum system remains unaltered. So this gives an impression that 2 colliding photons merge directly into a single one. So Here the levels shown in the figure by dotted lines are the virtual states. These are the virtual, what we were talking about. So this is second harmonic generation. And for efficient transfer of light energy from the pumping wave to the secondary wave, the condition of wave synchronization has to be satisfied. The pumping wave parameter should match with those of the secondary wave. In photon terms, this is equivalent to energy momentum conservation, where we are saying that h cross omega plus h cross omega is equal to 2h cross omega, or we can write out P1 plus P2 is equal to P. So assuming that the directions of the pumping wave and the second wave are the same, and therefore in scalar form, if the directions are same, P1 and P2, you can replace it by twice of P1 is equal to P. So P is equal to h cross omega upon C. And since we are talking about the frequency conversion from omega to 2 omega, so we have written here efficiency of this omega and efficiency of this omega. These two have been written with twice of omega. So look at this equation, P is equal to h cross omega upon C eta omega, so that twice of h cross omega upon C eta omega is equal to this 2 we have with omega. So this is giving you twice of omega. So eta omega corresponding to eta twice omega. So the figure shows the 3-photon process in which 1 photon of energy h cross omega is absorbed by the microscopic system, and the 2 photons with energy h cross omega 1. And I am talking about reverse of this, where h cross omega is falling on the material, and we get the h cross omega 1 and h cross omega 2. So I don't want to go into the detail of these processes. Of course, these processes are very important when we talk about the 2-photon processes, 3-photon processes, and parametric generation of light, where we are talking about the frequency conversion. So in 2-photon absorption, because this is the these slides I have chosen to display only because we are making use of 2-photon absorption. As I told you in optical limiters, I am going to the previous slide where I talked about the 2-photon okay. So a single photon absorption occurs between states of opposite parity, and in nonlinear medium, a 2-photon absorption occurs between states of the same parity. So that is a transition that is forbidden for 1-photon absorption is allowed for 2-photon absorption. So the probability of 2-photon absorption is proportional to the 4th power of the electric field. So this is very important, that the probability of 2-photon absorption is proportional to 4th power of the electric field. 4th power of the electric field means square of the intensity. So whatever the intensity we are calling on it, the square of that intensity gives us the probability of 2-photon absorption in that particular material. So another concept was saturable absorption and the reverse saturable absorption. For this, nowadays, whole of the world is using the nanoparticles, where nanostructured materials have unique physical and chemical properties as a result of their small size. So these properties differ largely from those of the corresponding single molecule and bulk materials. So a shift saturable absorption to reverse saturable absorption is observed at high input pump intensities. So again, I am saying that at higher pump intensities, only these processes are possible. So this happened only with the invent of lasers after 1960. Here the transition process was analyzed using the phenometrical model based on nonlinear absorption coefficient and the saturation intensity. In bulk medium, the magnitude of any nonlinearity is limited by diffraction effects. But in nanomaterials, we get away with the diffraction effects with particle size or the film thickness much smaller than the coherent length, thereby ignoring the phase matching conditions which we require otherwise in nonlinear processes. As I was talking about, the eta omega is equal to eta of twice omega. So that is one of the important phase matching conditions. So if we go with the non-materials, we can ignore these conditions and we can very well get the required results. As I tell you in the next slide, that with this, The total index of refraction now and absorption of the material is n is equal to n plus n2i, and absorption is beta naught plus beta 2i, where n naught is the linear refractive index or beta naught is the linear absorption, what we were calling about the two photon absorption, and I is the intensity of the light interacting with the material. So the important is to calculate these nonlinear parameters. What parameters we want to calculate? We want to calculate N2. Linear refractive index we can calculate with Abbe refractometer or with any other technique. Similarly, absorption coefficient linear we can calculate with ordinary techniques we have. But how to calculate beta 2? How to calculate N2? These are the challenges. So the refractive index of the medium, I have discussed about it, that refractive index becomes dependent upon the electric field. So we use beam distortion method or the Z-scan technique. Z-scan technique based on spatial beam amplitude distortion due to optical nonlinearity by propagation of laser beam within the medium. So better I come to this slide that we can put our nonlinear material here. We can focus our laser beam. We scan this around this focal point, and then we can see the transmission. So sometimes we get the focusing effect, sometimes we get the defocusing effect. That means sometimes we get the valley first and the top later, and sometimes we get the top first and the valley later. We use the open aperture scheme as well as the closed aperture scheme. Open aperture scheme gives us the absorptive effect, while the closed aperture scheme gives us the absorptive plus refractive effect. So the closed aperture scheme we can calculate the index of refraction. With open aperture scheme we can calculate the pure absorption. So this is how we use the nonlinear material. So in place of closed aperture Z-scan, to remove the contribution of nonlinear absorption from the Z-scan data, we divide point by point. And that means I am talking about the normalization of the data, how we capture the data, how we analyze the data, how we normalize the transmissions. So these are the two curves taken at 1064 nanometer in some nonlinear material. So there are fixed relationships available in the literature that N2 and beta can be calculated. So I will not go into the detail of these. So these are some of the relations available, and the pioneer worker has been the Sheikh Bahai, and people are harnessing the concepts given by Sheikh Bahai, and real and imaginary part of chi3 can be calculated. Our ultimate aim was to find out chi3, and we can find out chi3 by knowing N2 and beta. So this equation has been derived quantum mechanically. If you go for the second and third terms of this equation, you can see R. This is the particle size. As I was telling you that if we go for the nanoparticles, if we go for the size reduction, then there is enhancement of the susceptibility, because it is in denominator 1 by r, and it is also in denominator in the third term as 1 by r square. And if we go on decreasing the size of the particle, the susceptibility increases. That means simply in case of nanomaterial, the susceptibility increases. So people are trying to get the optical limiting response and optical nonlinearity in case of the nanomaterials. This is one optical limiting response, just to show a glimpse. In germanium, selenium, antimony, in polyvinyl alcohol composite film at 532 nanometers, the results have been taken up, and by changing the different compositions and different intensities, we have calculated the data, and this is the normalized transmittance versus input fluence. So this is how we can do it. The nonlinear transmittance by TPA is given by these two formula. Alpha is the linear absorption coefficient, beta is the nonlinear absorption coefficient, and L is the sample thickness. So Nowadays, people are working on chalcogenides, and chalcogenides are very important material nowadays, but they have the limitations because they are brittle. They are brittle. So we need to find out some host matrix for these glasses to use. Although these are advantageous in transparency for IR region, particularly IR region, as you can see silica in comparison to silica. So we need to use chalcogenide glasses if we want to go for the IR region. Defense persons are looking for this range of IR around 20 micrometer or 22 micrometers. So their telluride or selenide glasses are very important. So chalcogenide structures occupy a particular space among semiconductor materials. They are highly transparent in an IR, efficient emitters, and special interest are studies of nonlinear optical properties in the spectral range in which they are opaque. And we can use a modification of this scan technique. That means reflections this scan we can use if we will be using the 532 nanometer of the laser, because in the visible region they are not opaque. They are transparent IR region, and in visible they are opaque. And where they are opaque, we'll be using the reflection G-scan technique to characterize the material.
Not able to listen to you. Hello?
Yes.
Okay, now okay.
Yeah, you want to say something, Dr. Ghotal?
No, we were not able to listen to you. Now okay.
Okay. Should I go back to my slide? So, characteristics of chalcogenide glasses we have discussed. So, ultra fast response time of chalcogenide glasses is also one of the important things. So, ability of composition variation, where we can have the flexible structure. Properties can be modified by desired specification. So, doping is one of the important things that rare earth doping we can do with these chalcogenide glasses, radium, jolum, etc. So, high chemical and time stability, radiation durability, and non-toxicity. So, significant ionic conductivity, easy to prepare in bulk and layered form. And what we look for, always low cost. So, possible mechanism of nonlinear refractive index are influence of thermal effect that compete with the electronic process when wavelength corresponding to linear absorption, and the ratio of the radius of transverse cross section of the beam to the speed of the sound in materials is also very important. It is much higher than the pulse duration of the pulse. So these materials are also good for optical switching also. So I think I am running off the short of time, so I'll not go much into the details of this optical switching. So what I need, I will conclude. What we need for photonic technology, we need stable laser sources, and thanks to the optical technologies development, where we have nowadays semiconductor lasers as well, but they are of low power, and non-linearity requires a high power. So high power portable is a need of the day, and this is one of the major challenges. Second is high-speed transmitter, highly sensitive receivers, onboard optical processing systems, and optical clock distribution, as in case of GPS systems we require. So we want to explore UV, mid, IR range of the spectrum, and that means particularly of sun. So with these remarks, I think there may be discussion for 2-3 minutes. Anybody who wants to ask something?
Yeah, thank you very, very much for so enthralling lecture. Yes, we will pick up question, and I request all the participants, please, whenever you will be asking your question, you put your microphone and directly ask the question to the speaker. Please, go ahead. Participants are requested to ask questions if they have. You can ask directly without putting in chat box. Any question from the participant side? Anyone wants to ask any question?
It seems we have understood everything.
Okay, if there are no further questions, then on the behalf of Faculty of Science, University Technology, Malaysia, we are very much thankful to Professor Devendra Mohan for his wonderful lecture and valuable time with us. Previously also, he has accepted all our invitation and have given wonderful lecture, highly knowledge gaining type of lecture for our student and young staff. So we'll see you again, and let me just share my screen by showing your certificate for this particular presentation. Can you please switch off your sharing screen, please?
Yeah. Just I wanted to comment that earlier there has been a saying that laser is a solution in search of a problem. But now I have changed the statement that photonics is a solution in search of a problem. So with these remarks, I thank you, Dr. Ghoshal, you and your team, and who are arranging and who are doing wonderful things for the students. And I understand that these students and the faculty must have got some terminology which they can explore further. So there are optical isolators, as I was telling, that certain components which are being developed and need of the hour. So small parts we can pick up for our research areas. So I think I will be putting some of the things on my YouTube channel, so one can go for that also in coming days to come.
Thank you so much for your valuable comment and contribution. We'll discuss this. We will take a note of it, and it would be useful really. So I hope you can see your certificate.
Yeah, I can see the certificate. Thank you very much.
This has been sent from Faculty of Science through your email.
Okay.
So you please accept our regards, and for the future we will invite you again and again. And I request entire participant to join hands with me, and thanks Professor Devendra Mohan for his wonderful talk. Thank you very, very much.
Thank you everyone. Thank you.